All right, welcome. Today, we're going to dive into a core idea in science that kind of turns common sense completely on its head.
I mean, just think about that for a second. That one question, it gets to the heart of a really powerful method for thinking more clearly and, maybe more importantly, for avoiding one of the most common mental traps we all fall into.
You know, we're all taught to look for evidence that backs up what we already believe. But what if the real power, the real secret sauce, isn't actively trying to find evidence that just completely shatters our beliefs? It sounds kind of backward, right? So let's get into why this is so critical.
Okay, so first, let's look at how we usually think science works. This is the method of induction. It just feels right, doesn't it? You see a bunch of specific things and you build a general rule from them. It's totally intuitive. But, and this is a huge but, this method has a fatal logical flaw baked right in. Yeah, think about it like this. You could spend your whole life observing 1 million, 10 million, 1 billion white swans, but you can never, ever be 100% certain that the very next one you see won't be black. That's the classic problem of induction. No matter how long your list of observations is, you can't logically prove a universal statement is true. It's just impossible. Okay, so this is the huge problem that philosopher Karl Popper walked into, and he came up with a revolutionary solution. We need to adopt what he called the critical attitude.
So the big idea here, falsifiability, is that the true sign of a scientific theory isn't whether you can prove it's true. It's whether it's even possible for an experiment to prove it false. The whole goal shifts. You propose an idea, and then you try with everything you've got to destroy it, not to defend it. If a theory can't be tested and potentially shot down by reality, well, then it's not really scientific.
This analogy, it just makes everything click. Think like a bridge engineer. Seriously, do you learn more about how strong a bridge is by counting the thousands of cars that cross it safely every day? Or do you learn more by finding that one single point where it finally breaks under stress? Of course, it's the breaking point. That's where the real knowledge is.
All right, so if the goal is to break our theories, how do we build them in the first place? Well, the trick is to build them in a way that makes them strong precisely because they're so easy to snap.
This quote from Popper just nails it. A theory's real value comes from what it rules out. A powerful law of nature isn't powerful because of what it allows to happen. It's powerful because of what it forbids. It makes these huge, bold claims about the world by saying, nope, this will never, ever happen.
So, you can see how this works. The best theories are these big, universal claims, they're super precise, and they're simple. And why is that? Because all those things make them much, much easier to break. Think about it. A vague theory, one that's full of loopholes, can explain away almost anything, which means it doesn't really explain anything at all. But a bold, precise theory, it sticks its neck out on the chopping block. It makes a clear claim that we can actually go out into the world and test, and that's exactly what makes it so valuable.
Okay, so we've got our bold, breakable theory. Now what? How do we actually go about testing it? Well, it's all about designing the ultimate test, an experiment that isn't trying to confirm, but to challenge. And this is the process. It's basically a logical hunt. You're not just wandering around hoping to find more white swans. No way. You are actively setting up a search party with a map and a mission to find a black one.
And the logic behind this is just beautifully simple. It's a tool called modus tollens, and it's the real engine of science. Unlike that messy induction stuff, this is a totally valid, rock-solid argument. If your theory says X must happen, and you run the experiment and X doesn't happen, well then your theory has to be wrong. It's clean. It's decisive. Boom.
But, you know, we're human, right? When a test fails and our pet theory gets shot down, isn't our first instinct to get defensive, to protect our idea?
Absolutely. And that's where that pesky confirmation bias sneaks right back in. Which is why you need strict, hardcore rules to keep yourself honest. And the rules are tough for a reason. You see, a successful falsification, that's not a personal failure. It's a scientific success. It's like finding a giant error on a map. You wouldn't be mad, you'd be thrilled, because now you have the chance to draw a much, much better, more accurate map of how reality actually works.
So, what do we call a theory that survives all of this? I mean, a theory that we've tried our absolute best to destroy, and it's still standing.
The word is corroboration. And notice, we are not saying it's verified or proven true. Not at all. It has simply proven its mettle. It survives some really severe testing. For now, it's been battle-tested and it's still standing.
So let's go back to our bridge analogy one more time, because it makes this difference between confirmation and corroboration perfectly clear.
A million confirmations might make you feel safe and secure, but what does it really tell you about the bridge's ultimate strength? Honestly, not much. It's just a whole lot of low-quality information.
But now, what about one single severe test? Like, say, the bridge survives a direct hit from a Category 5 hurricane. Whoa. That one event, that one test, tells you more about the bridge's true resilience than a million cars ever could. That, right there, is the difference between simple confirmation and powerful corroboration.
And that's really the heart of it. The true value of a theory isn't how long it's been around or how many people believe it. It's the severity of the attempts to break it that it has survived. It's a measure of mettle, not a certificate of absolute truth. It tells us which of our ideas are truly robust, not because they've never been challenged, but because they've faced the toughest challenges we could possibly throw at them and come out the other side.
So this whole way of thinking, this critical attitude, it's not just for scientists in a lab. It is an incredibly powerful tool for any of us who want to get a little bit closer to the truth. By actively seeking to falsify our own assumptions, we don't actually weaken our beliefs, we make sure that the ones that survive are truly the strongest ones we have.